Hello, my name is Trinity Glover. I'm in section 11, and this is my protein project. The protein I was assigned was KRas. And before I talk a little bit about my model, let me briefly go over what KRas is. So KRas is a relay molecule and for cell signaling, and it is a part of the signaling pathway known as the RAS MAPK pathway. And what this protein does is that it relays signals from outside the cell to the cell's nucleus. These signals instruct the cell to grow and divide, or carry on different functions for like differentiation. And so the KRAS protein acts as a off and on switch by converting GTP into GDP or vice versa. So GTP acts as an on switch and GTP acts as an on switch and GDP acts as an off switch. So as I say that, I want to showcase my my model. And so the red here, let me start by saying that this model was made purely off of stuff that I already had in my dorm. I wasn't able to go out that much. But anyway, so different colors act for different things. Since we're talking about switches, I'm going to go ahead and mention that this is pipe cleaners. I use the pipe cleaners to basically use these as a way to indicate what's a switch and what's not. So the red is the switch 1, and then the blue is switch 2. These are the switches that kind of turn on and off the KRAS protein. And this right here, over here, hold up, this is the GDP. So right now, this protein is in a off state. This is the GDP. It's right here. It's in orange. And of course, because it's a protein, we have to have our P loop. Our P loop is highlighted in with yellow pipe cleaner. Oh, and I had used clay to indicate the membrane of the protein. So the pink yellow clay in the middle is the membrane of the protein. Okay, let's continue. So RAS protein, or it's not something, how should I put this? RAS protein doesn't act by itself when it switches on and on. RAS protein is used to help of other complex proteins to kind of help aid switching on and off. So let me briefly explain that. So we have a GF protein. It's not in this model right here, but this is a little background information. So you have the GEF protein, which turns on the RAS switch, and then they kind of wrench open the binding site, allowing GDP to escape, which is this right here. It's highlighted right here. And then once GDP escapes, GTP can come in and bind to the empty site. I would say this is represented GTP right here. And after that, once GTP has bounded to the empty site, it interacts with effectors like PI3KY, and that's a lipid kinase. And then when that happens, when it's time for the RAS to switch off, it basically slowly breaks down GTP and then goes back to GDP, but the GAP, the gates, it's like a GTP, it's like a activating protein. It helps like speed up the process, because converting from GTP to GDP is a very slow process. Okay, moving on, I want to talk a little bit about the mutations that you can expect from a protein like this. So if you don't already know, KRas mutations play some of the most important roles in cancer, especially lung cancer in specific. And how this happens is that there's this type of KRas mutation. It's called a KRas G12C mutation, and it accounts for about 44% of all KRas mutations. And the G12C is a single point mutation with a glycogen to cytosine substitution, and that substitution happens at carbon 12. It's mindful to note that this substitution does favor like the active state of KRas. So this basically amplifies the signaling pathways and basically instructs the cell to like keep growing and dividing. And when you have uncontrolled cell growth, it can cause tumors, and tumors can lead to cancer. Another way to describe this favorable substitution is something that's called oncogenesis. I don't know if I'm saying that right, but basically, to clarify what that means, if it's not already known, is that oncogenes, they are genes that are closely linked to cancer, and they are also the genes that encode RAS. So mutations of the oncogene changes the functions of the encoded protein. And so it creates like different properties and basically instructs the protein to like stay in an activated state. And when KRas is in an activated state, it constantly sends signals from outside the cell to the cell's nucleus to kind of basically continue the process of cell division. And again, if I haven't already said it, or if I'm just repeating myself, this causes rapid cell growth and like uncontrolled cell growth, and this can lead to tumors and in turn cancer. So this was my protein project. Again, let me clarify. This is the membrane of the KRas. The red was switch 1 and the blue was switch 2. Because I didn't have enough material to make 2 models, I just highlighted the GDP in orange and the GTP in blue here, as you can see. And then this is the P loop. Thank you.